So we've come up with three unsolved mysteries to do with the first light in the universe. One is the question of just where are the first stars? Some of these first stars should still be around. They should be very easy to see because they're completely lacking heavy element absorption in their spectra, but we do not see any. We see the second generation, but first generation, no. Second problem is a timing one. The quasars seem to indicate that the universe was mostly reionized about redshift 6, but the microwave background scattering indicates it happened rather earlier, before redshift 10. The third problem is what actually causes reionization. We need lots of ultraviolet to do it. There certainly don't seem to be enough quasars to do it. Stars, it's a bit more rubbery, but they still also seem to be lacking enough to see it. So let's deal with these things one at a time. So maybe let's start off with the question of where are the first stars? So Brian, we haven't seen any of these first stars. What's your take on this?
So one of the reasons it's so hard to calculate when the first stars appeared is because it's not just gravity. It's really pressure and all the complicated weather that comes along with atomic physics and pressure and shocks and things. And so one of the big questions is when things compress, they heat up. And in order to form stars, you have to be able to cool. That is, you need to be able to have somehow the gas cool so it can get dense enough to actually get the first stars. And it's thought that because when you cool, you usually cool through atomic transitions of not hydrogen and helium, but things like oxygen or iron, that since that stuff doesn't exist in the early universe, maybe the first generation of stars are very different than subsequent generations.
So what you're saying is that when a star forms nowadays, we'll talk about star formation a bit later, the gas cloud can cool by radiating using these heavy element lines, but that can't happen in the universe. So how might the stars be different?
Well, to first order, you would think that you might get much bigger clumps forming rather than little ones. That is, the cooling allows little clumps to effectively form easier than the big ones. And it may well be only the biggest clumps can form stars. And that might indicate you get a generation of, 500, 1,000, or even 10,000 times the mass of the sun stars, things that we just simply don't see today.
Well, that solves our problem then, doesn't it? Because the big stars will collapse, form black holes and some small amount of heavy elements, but they won't still be around because, as we've said, massive stars don't last very long. And if we're not forming any small ones, it's the small ones that would still be around, so surely that solves the problem. There were only massive stars, they've all exploded long ago, they've dumped out heavy elements and therefore given the second generation that we see.
So it sort of solves the problem, but it sort of doesn't, because when we do look at those second generation of stars, we can see sort of, what they're made out of. And the chemical elements they're made out of seem to be exactly what you expect from kind of bulk standard supernovae. Nothing exotic like a 100 or 1,000 solar mass exploding star, which would produce very different element combinations than what we see. So it seems that this idea has a problem. We don't see really massive stars being the things that enriched these second generation of stars we see.
So for our first problem, where are the first stars? We have a solution. The solution is maybe they only formed big stars early on and not the small ones which would still be around. But that solution, as so often is the case in astronomy, has raised a whole bunch of new problems. They should have produced weirdo ratios of elements, which is not what we see in the second generation of stars.
That's right. So I think what we need to do is, because we only have a few of these second generation stars, we need to see more, but we also probably need to have better theory of how those first stars really did form.
So then we go on to the second problem, which is, when did the universe become reionized? Was it reionized at redshift 6, as the quasars seem to say, or was it up at redshift 10, 15, 20, like the microwave background scattering indicates? What's your take on that one?
Well, there's two ways to look at it. One is that the universe became reionized really in a very complicated way. When we looked at trying to estimate what time there was enough electrons there for the universe to make that transition from being neutral to ionized with the cosmic microwave background, we assumed it all happened at once, that the universe sort of went from being neutral and then click, it turned the switch and it became neutral. And you can calculate it very simply then. Maybe it was much more complicated, and that's the problem. Alternatively, those quasar measurements, it turns out that we're sort of fudging it a little bit because you need so little neutral hydrogen in the universe to block out all the ultraviolet light, really only 1 part in 10 to the 4 of the hydrogen being neutral to do it. Maybe it's just that at a redshift of 6, we're seeing 1 part in 10 to the 4, and it really does take to a redshift of 10 for that transition to really occur.
So maybe what you're saying is it's kind of like a drawn out or a two-step process, that maybe most of the hydrogen was ionized up at redshift 10 or 15, whatever we need for the microwave background, but there was still a very small fraction that was neutral down to redshift 6, and that small fraction was all you need to block the quasar light.
That's right. So it could be one or the other, and those are both very different outcomes.
Okay, so once again, we're part of the way towards a solution, but not fully there. And then we get on to the third mystery, which is what actually was doing the reionization. We can look out to about redshift 7, and there's certainly nothing like enough quasars, and probably not enough stars either. What's your take on this?
Well, I think the problem we have is right now we cannot see individual stars. We really have to look at galaxies. And we have every reason to believe that the first crop of galaxies were very small. And if so, if the universe is divided up into tiny little parcels, there could be huge numbers of tiny little galaxies that we just simply can't see. So one could imagine, maybe with the James Webb Space Telescope, which really is getting to the point of seeing individual stars, maybe we'll get a clue that there are vast numbers of little galaxies, or maybe we genuinely have some other way to ionize the universe, some sort of, for example, dark matter, or something that puts out ultraviolet photons, or some crazy thing we can't really envision at this point.
So how are we going to set about answering these questions? We talked about the James Webb Space Telescope, which in principle might be able to see some of these first stars, assuming they really are up at the many thousands of solar mass type size. How about ground-based telescopes?
Yeah, so there's this new generation of extremely large telescopes. So here at the ANU, we're working on the Giant Magellan Telescope. There's also the 30-meter telescope and the European Extremely Large Telescope. These next generation of telescopes are 25 to 40 meters in diameter, so they're huge. And one could imagine that if James Webb Space Telescope can find things, these big telescopes can take their spectra and try to puzzle together how all these questions come together, maybe even literally see individual first stars. That would be a huge leap forward.
How about the radio astronomy? You've talked about the Murchison telescope and how it may or may not be there. You won't find out for a couple of years. If it doesn't find the side of this hydrogen going away, what's the next step there?
Well, one can imagine building a huge telescope, for example, a square kilometer of collecting area. And such telescope really should be able to see hydrogen in the dark ages. And so one could imagine looking back, seeing the hydrogen, and when you can see the hydrogen in radio, you actually know how much is there, and literally watch the universe go from being full of neutral hydrogen to being empty of it. And such a big telescope, which is probably at least 10 years away, has the power of literally seeing the universe turn on directly.
So really there's grounds to be quite optimistic here. Unlike some of the other mysteries we've been talking about, there's lots of reason to believe that 10 years from now we're actually going to know the answers to these things.
Yes, we have the benefit here of technology really opening up this field of astronomy. And astronomy, of course, really has been driven from day one by technology. And I have every reason to be optimistic that over the next decade or so, we really will understand how the universe went from nothing to the glorious place that we live in today.